Today we're talking about graphing absolute value functions. An absolute value function is a function that contains an absolute value expression. The parent function for any absolute value function is always f of x equals the absolute value of x. And the graph of f of x equals the absolute value of x is always v-shaped and symmetrical about the y-axis. The vertex of an absolute value function is the point where the graph changes directions. So the vertex of the graph f of x equals the absolute value of x is at 0, 0. When we say that an absolute value function is in vertex form, what we're saying is that it's written in the form g of x equals a, which is a constant, an absolute value x minus h, where h is a constant, plus k, where k is also a constant. And a cannot be equal to 0 when it's in vertex form. When you see an equation in this form, you can easily identify your vertex because it's going to be your h value, comma, your k value. And the graph will be symmetrical around the line x equals h. Here we're being asked to graph each function and compare the graph to our parent absolute value function, f of x equals the absolute value of x, and then describe our domain and our range. So on both of these graphs, I've already graphed the parent function. So f of x equals the absolute value of x. That's my line in green on each of these, okay? But now I'm going to use some input values to graph this g of x problem, the absolute value of x plus 3. So if I plug negative 2 in here, I'm going to get 2 plus 3, which is 5. If I plug in negative 1, I'm going to get 1 plus 3, which is 4. If I plug in 0, 0 plus 3 is 3, and you probably are starting to notice a pattern emerging. 1 plus 3 is 4. Oh, I'm going back up. 2 plus 3 is 5. So let's graph these points so we can see our g of x. So I've got negative 2, 5. I've got negative 1, 4, 0, 3, 1, 4, and 2, 5. So it looks like my original V shape, except this is a translation. So our entire graph has moved up 3 units. So it's a translation, a vertical translation, 3 units up. Our domain can be anything. Our x values, it keeps growing, they can be anything. So we say all real numbers. But our range on this graph, our y values can't be less here than 3. So our y values are greater than or equal to 3. All right, let's take a look at this one. So this time, I have my parent function graphed here. Now I'm going to graph m of x, and it's the absolute value of x minus 2. So I'm going to plug some things in. 0 minus 2 gives me negative 2, absolute value is 2. 1 minus 2 is negative 1, absolute value of 1. 2 minus 2 is 0, 0 is its own absolute value. 3 minus 2 is 1, so 1 for my absolute value. 4 minus 2 is 2, absolute value of 2. So let's graph this one. I've got 2, 0, 3, 1, and 1, 1, and 0, 2, and 4, 2. So once again, we've kept that V shape. We have another translation, except this time our entire graph has shifted 2 units to the right. So it's a translation 2 units right. So once again, the x value is the domain. It's growing. They can be any number. So we say all real numbers. And my range, everything is 0 or above. So our y values are greater than or equal to 0. All right, once again, we're graphing and comparing to our parent function, which is f of x equals the absolute value of x. So that equation has already been put on the graph here in green. It's my parent function. So now I'm going to plug in some values into this function q. So I'm taking the absolute value of my input times 2. So the absolute value of negative 2 is 2, times 2 is 4. 1 times 2, 2, 0 times 2, 0, 1 times 2 is 2, and 2 times 2 is 4. So when I go to graph this one, I've got 0, 0, 1, 2, 2, 4, and negative 1, 2, and negative 2, 4. Oops. So it's the same V shape, except it's going up quicker. It's actually a vertical stretch. So my domain here can still be all real numbers. It could be anything on the x-axis. It keeps growing. And my y values, my range, nothing is lower than 0. So y is greater than or equal to 0. So a vertical stretch by a factor of 2. All right, so let's take a look at this one. So we're going to plug some things in. This time I'm multiplying by negative 1/2. So I'll put the absolute value of my input in there. So negative 2, I get 2. 2 times negative 1/2 gives me negative 1. My absolute value of 1 is 1 times negative half, negative 0.5. 0 times negative half, 0. 1 times negative half, negative 0.5. And 2 times negative half, negative 1. So I still have got my 0, 0. So I still have my V shape, except it flipped upside down. When I multiply by a negative, I'm going to have a reflection over the x-axis. And this guy, this V, he's not growing quite as quickly. He's a vertical shrink by a factor of 1/2. So my domain is still all real numbers. It's still growing, and the x can be anything. But since my graph flipped this time, the y values have to be less than or equal to 0. Less than or equal to 0. All right, this time I was asked to graph a different parent function. So as our parent function, we're going to have f of x equals the absolute value of x plus 2 minus 3. So I had some inputs here. I plugged them into my equation, and I listed my outputs, and then I graphed it right here on this graph. So one interesting thing about this equation, it's almost in vertex form. So we have f of x equals x, if I made this minus negative 2 plus negative 3, I would have this in vertex form. And I can see that my vertex is going to be negative 2 comma negative 3. That's right here on my graph. This guy then is symmetrical across the line x equals negative 2. So if I drew an imaginary line at x equals negative 2, I'd have it going this way, and it would be a reflection symmetrical on both sides. So now they're asking us to graph g of x, and that's the absolute value of 2x plus 2 minus 3. So let's plug our inputs in here and find our g of x values. So negative 4 times 2 is negative 8. Negative 8 plus 2 is negative 6. The absolute value is 6 minus 3. I get 3. Negative 3 times 2 is negative 6. Negative 6 plus 2 gives me negative 4. Absolute value is 4. Minus 3 is 1. And I'll just keep going with these. I'm plugging in negative 2, and I get negative 1 as my answer. I plug in negative 1, and I get negative 3 as my answer. I plug in 0, and I get negative 1 as my answer. I plug in 1, and I get 1. And I plug in 2, and I get 3. So let's graph these points. Got negative 4, 3, negative 3, 1, negative 2, negative 1, negative 1, negative 3, and then it grows going this direction. got a little bit off there, my graphing. But we get the idea. So they want us to compare the graphs here. So I notice that if I compare these two, the only thing that's really different here is that I'm multiplying my inputs by 2. So really, I could write my g of x equation. The only thing that's different is I take my inputs and I multiply them by 2 before. That's the only thing that makes it different from the f of x. So if I multiply my inputs by 2, I'm going to have a horizontal shrink by a factor of 1/2 because it's the reciprocal here. So it's shrinking, which is kind of causing it to move over, but it's also by a factor of 1/2 if I look at my coordinates. Finally, one more here. They want us to identify the transformations before we actually start here. So our g of x is -2 times the absolute value of x minus 1 plus 3. And it's from our parent function, f of x equals the absolute value of x, which I've graphed right here on this graph. I found some output values and graphed it. So when I look at this guy, I can tell from this -1 right here on my inputs that I'm going to horizontally translate this graph. So I have a horizontal translation. Everything here is going to move 1 unit to the right. So I have a horizontal translation. One unit right. Everything's going 1 unit to the right. I also have this plus 3 outside of my absolute value. That's going to vertically translate my graph. I'm going to go 3 units up. Now I'm multiplying by -2, so I'm going to have a vertical stretch. By a factor of 2. And since it was a negative, it's actually going to be a reflection over the x-axis. So now let's graph g and see if our prediction is actually correct. So we're going to plug some things in. So -1 minus 1 gives me -2. Absolute value is 2. 2 times -2 gives me -4, plus 3, I get -1. If I plug in 0, 0 minus 1 is -1, absolute value is 1, times -2 is -2, plus 3 gives me +1. If I plug in 1, 1 minus 1 is 0, 0 times -2 is 0, plus 3, 3. If I plug in 2, 2 minus 1 is 1, 1 times -2 is -2, plus 3 gives me 1. And if I plug in 3, 3 minus 1 is 2, 2 times -2 is -4, plus 3 gives me -1. So -1, -1, 0, 1, 1, 3, 2, 1, and 3, -1. So it definitely is a reflection over the x-axis, but a few things happened first. So first this guy went 1 to the right and up 3. Then it was flipped after that. We also notice that it is stretched. It's growing quicker. It's a much narrower V than the one that we had here. So our predictions were correct. Our vertex for our g function is right here, and it is at +1, 3.